Welcome back to this session. I'm Masahiro Hotta. I'm a chair of this session. So we are very happy to have Philipp Höhn from OIST. So he will talk about dynamical frames in gauge theory and gravity. So please go ahead.
Yeah, thank you very much. And also thanks very much to the organizers for putting together such a wonderful workshop. And having me. So I'm very happy to be here and meeting many of you in person. So since this is a rather diverse workshop, I've decided to give more of an overview talk. So I'll provide some intuition and try to be didactic on many of the cases that I will discuss to give you some overview over dynamical frames in gauge theory and gravity, in particular, so that there will also be something in this talk, hopefully for everybody here. So this talk will be mostly based on the first three papers here, and perhaps towards the end, I will also manage to talk about the last one, which is actually in quantum reference frames. The bulk will be about dynamical frames in classical field theory. So yeah, the main reason we of course care about reference frames is usually that, if you want to have some concrete description of the physics, that we need some kind of references in the game. And the very fact that we need to do this, of course, tells that there's some ambiguity, and the way we usually get around ambiguities is by some kind of covariance principle or relativity principle that's associated with some kind of group under which frames transform. Now, this is of course also true in gauge theories and gravity, but there's something special in these theories that feature a gauge symmetry, and that is that they lead to some kind of relationalism. And what I mean by that is that physical statements, and by that I mean in particular gauge invariant statements, require to resort to some kind of internal or dynamical reference to make sense. And the gauge-induced redundancies, they tell us that there's in general no unique such internal references, and ultimately that leads to to gauge invariant descriptions that however depend on the choice of an internal reference. And these gauge invariant descriptions, they're also, of course, often non-local. And these are facts that are generally appreciated, but what has not been often really spelled out is how to identify actually from this notions of really properly dynamical reference frames that are associated with the gauge group, and also to ask how we can, for instance, transform systematically from the description of one relative to one dynamic reference frame to that of another. Is there something like a dynamical frame covariance? And in particular, in the quantum theory, this gets interesting because when these frames are dynamical, they're going to be quantum, and that means they're subject to fluctuations, and there will be in relative superposition to one another. And so this is a bit the aim here to discuss this. I will, as I said, mostly focus on classical field theory because there's still some gaps that we have to understand better before we go to the quantum theory. So in recent years, we made a lot of progress on the quantum side, but more in mechanical models. And in order to extend this to field theory, there's a couple of things we need to understand better on the classical side. In particular, we'll also be talking about locality in these field theories. So just to provide you a bit of intuition that even in internal frames and gauge theories have physical significance, let's look at a simple example. And suppose there's some kind of electrician wanting to measure voltages of different parts in electric circuits. Well, this is in general not possible without you referring to some kind of reference. And if there's perhaps a second electrician, depending on how they're charged, they may give quite different accounts of the same parts of the circuit, and maybe they get a shock, and maybe the other one doesn't. And so what is important maybe here in this example is that well, first of all, these two electricians, they might give very different accounts of the same parts of the electric circuit. They're gauge invariant because voltages only depend on the electric field. They try to describe the same thing, but they give quite literally different accounts. One might get a shock, one doesn't. And on the other hand, these voltages already also give you an illustration, of course, that gauge invariant statements are somewhat non-local. Here you have a line integral. So, but now more generally in gauge theories, we can ask, for instance, about measuring charged objects, and by the very nature of them being charged, they transform non-trivially under gauge transformations. And therefore, in order to come up with gauge invariant statements, we actually have to provide again some kind of dynamical reference. And for instance, in this case, sorry, for some reason the slides are not really moving, but yeah. But here, for instance, in this case, one way in which you could measure such, let's say, an antiparticle is by connecting it with a Wilson line to some positive charged particle. It turns out that that will be gauge invariant. And in this case, you can, for instance, view this positive particle, including the Wilson line, as being the dynamical reference for that particle, or you can also view it vice versa, of course. And again, of course, in general, if you want to measure that or describe that antiparticle, it will be many different ways. You could have chosen maybe some other particle and some other Wilson line to describe it. And that is a gauge invariant description, but it depends on a different dynamical reference. Okay, so that's in the coming slides, I'm going to be focusing more on gravity. And in fact, most of this talk will be about gravity. So here the gauge theory, the gauge symmetry is diffeomorphisms, bulk diffeomorphisms. They move space-time points around. That makes locality much more challenging. And so if we have some kind of diffeomorphism F, so what I should say is if I use square brackets of phi, that just means it's a function of the fields, and phi is just a collective notation for the fields involved. And so if I want to look at some observable, what we want is gauge invariant observable. So if I look at evaluating that observable on gauge transformed field configurations, it should of course be the same as under the untransformed one. And often it's said that it's very difficult to construct such gauge invariant observables in gravity, but in principle, it's at least at a formal level not true. So as long as you have some covariant top form that so transforms in this way under diffeomorphisms, bulk diffeomorphisms, you can just integrate it over all of space-time, and then by some integral identities, you'll find that this is true. And of course, one example is when alpha is the Ricci scalar, then this whole thing is just the Einstein-Hilbert action, which is gauge invariant. But when you look at such objects, they are a priori, of course, extremely non-local. And the real challenge is how do we construct phenomenologically interesting gauge invariant observables with some kind of local information. And that there is some kind of tension between locality and gauge invariance is something you can already see in a very simple example of a scalar field. So it transforms like this under diffeomorphisms. And that already tells you that if you want to, that phi of x, the field at some point x, is only going to be gauge invariant if phi is a constant in spacetime, maybe a cosmological constant, or if x is a boundary point where gauge diffeomorphisms might act trivially. So that leads to some tension between the usual notion of bulk locality in terms of fixed references or fixed labelings that we're familiar with, for instance, from quantum field theory, and gauge invariance. And now what we want to do is, one could wonder about what we adapt in order to get around this, and we're definitely not going to give up gauge invariance. And so what we have to do rather is to adjust our notion of locality to be able to live with this. And so if you think about this here, what really fails, or the notion of locality that fails, was one with fixed, one based on a fixed labeling. So it's a non-dynamical labeling. And so it's really one that's based on fixed reference frames, and in some sense, unphysical reference frames. And so to get around this, what we want to have is dynamical reference frames. And in fact, even Einstein was already aware of this. So here's a quote from him where he's basically saying that the series, so general relativity, introduces two kinds of physical things, measuring rods and clocks, so reference frames really, and all other things like the fields, blah, blah, blah. And this in a certain sense is inconsistent. Strictly speaking, we will want the measuring rods and clocks to be also, they should be represent as solutions of the basic equations. And so if we want to take this serious, so what we really want to have is not a fixed labeling of space-time events, but field-dependent or dynamical labelings of space-time events, so that they're subject to the equations of motion. And for instance, such that for bulk diffeomorphisms, they transform in this way. So I will explain more why that is true. So for instance, if you have something that transforms in this particular way, and then you look at now coming back to the scalar field, and you want to ask what's the value of the scalar field at a point defined in this way, then just by looking at how the two transform at diffeomorphisms, you'll see that that's going to be invariant under bulk diffeomorphisms. So and then this is now the value of a scalar field at a dynamically defined event. And in fact, to provide you a bit of intuition of how one could achieve something like this, so what we want to have is dynamical coordinates for space-time, really. And there's a very simple toy model that was developed by, or formulated by Giddings, Merrill, and Hadel about 15 years ago. They call it the Z model. And here, for simplicity, I assume there's 4 scalar reference fields. So they're dynamical ZK that parameterize, that they're in a configuration that parameterize spacetime. And then a way to realize this observable is really in this particular way. So basically, you put in the scalar field at some non-dynamical coordinates phi y, and then you put in a delta function that clicks when the fields read a particular value. Okay, and then the rest is just measures. And so this thing turns out to be a covariant top form, as I had it on the previous slide. So that is actually gauge invariant. And this is what you can call really a relational observable. It answers really the question, what's the value of the scalar field at the event x in spacetime where the reference fields take the value psi k. And now, when you think about this object here, it is non-local in a certain sense, but it's only non-local with respect to these fixed coordinates y. But it is local with respect to the dynamical event x phi, right? And so you can say it's local in the Z in Z space, or in this field reference field space. And so this is something that we want to develop more generally, and you can call that a relational notion of locality, where we're going to be localizing fields relative to one another in a gauge invariant way. And this is, of course, something that has been discussed since decades, going back to at least Bachmann and Koma. And has appeared in various forms in recent years, also in different communities. But if we want to have such a relational or really dynamical notion of locality, we better make sure that it's a consistent one, consistent with our experiences. And for instance, what we need to have, of course, is that we have a notion of gauge invariant local observables. So basically, more general forms of what I showed you on the previous slide. So there should be non-trivial observables associated with events in space-time. And now, if we have dynamical reference frames, what we would want to have is, of course, also just like in our standard notions of generativity, have a way of frame covariance. So we want to be able to translate between different dynamical frame descriptions. And in particular, so we can have a notion of general covariance in the sense where we can say that all the laws of physics are in fact the same in every dynamical reference, so in a physical reference frames really, rather than fixed frames. And when it comes to locality, important notions such as bulk microcausality should of course be respected, and this should be done now relative to frame really. So observables, relational observables should commute at space-like separation, and we also want to have a gauge invariant notion of local subsystems, so we can have all kinds of notions from quantum information theory or even thermodynamics that we can run in space-time. So now, hopefully, explain at least some of these things in the coming slides. I will be at times talking a bit about gauge theories but mostly about gravity. But now let's have a thought at first what we actually mean by a dynamical reference frame. So the dynamical reference frame will be some, field in our case that's associated with whatever the gauge symmetry group is. So in gauge theories or in gravity. And we want to use it to basically deparameterize the gauge orbits to use them as some kind of dynamical coordinate system. And we will call the configurations of this frame orientations of the frame. And these orientations, they can be, for instance, literally orientations of a tetrad or readings of a clock or whatever is appropriate in the given circumstances. And then for the purpose of this talk, I will be mostly restricting to special kinds of reference frames, namely those that are actually group valued, so that where the configurations or the orientations take value in the gauge group, and where the frames are gauge covariant in such a way that under the gauge group action, they transform in this way. So basically just by group multiplication. So you can describe more general dynamical frames than this, but that gets a little more technical. And anyway, so we want to use these frames then to parameterize G orbits and to construct frame dressed or relational observables, similar to what I mentioned before. And the way you can do it basically is you just use the gauge action on some observable you might be interested in, and you dress it by the inverse of this group valued frame. Okay. And then you can convince yourself that this thing is gauge invariant, but maybe let's not go too much into this. And let me just give you a warm-up, a quite simple one that really illustrates these ideas from special relativity, where you can see that you can actually formulate the usual notion of special covariance in this this language. From this, you can see a lot how it will proceed towards gauge theory and gravity later. So and what we'll be assuming here is that, okay, we have some fictitious or external coordinate frame, if you want, t, x, y, z. And we have some vector that we want to describe, and could be some velocity, some particle flying through space-time. And we, of course, have some Lorentz transformations acting on this. And here we're going to take in such a way that these, since these are fictitious or external coordinates, that these transformations are actually distinguishable relative to such a fictitious frame, but not relative to one that's internal. And what do we mean by an internal frame here? We can insert something like a tetrad into the game, and then we try to describe everything relative to the tetrad. And the tetrad itself, okay, that's basically, we're going to consider this, of course, the frame orientations. It comes with two indices, space-time indices and frame indices. And because of these two different indices, it comes with, in fact, two commuting group actions. And one we can call suggestively here gauge transformations. Those are the space-time Lorentz transformations. They act on all dynamical degrees of freedom if you want. But then there's also the frame index, and there's also Lorentz transformation acting on those. But these really only act on the frame. These we can suggestively call symmetries. And in fact, well, they're really frame reorientations. So if you look at what this does to the frame, it really reorients the frame. It changes the relation, for instance, between the frame and the velocity that we want to describe. Now, then, of course, when you look at normalizations of tetrads, it satisfies this condition here. And this means in particular that these tetrads are group valued. They're valued, for example, in the Lorentz group itself. So in that sense, they're actually group valued reference frames. And so here, the group really acts on itself. And now we can look at gauge invariant objects, and gauge invariant means invariant under these transformations. And while we just described, we contract the frame really with the tetrads. You only have now the frame index, and of course that's invariant under such transformations. And we can call that a frame dressed observable or relational observable, and it describes this velocity as seen by that reference frame. And now we can insert a second such tetrad into the game. And well, now we can also look at the transformation laws between the relational observable describing the velocity relative to the first frame and the second frame. And you can just simply do that by replacing, of course, the eta here by the normalization condition for the second frame. And this here is just the relational observable describing the velocity relative to the second frame. And this here describes the first frame relative to the second frame. It's also a Lorentz transformation. And yeah, so that's really the reference frame transformation between the descriptions relative to two internal frames. And it's important that this thing is a relational observable itself. And well, in this way, you can formulate the usual ways of covariance. Okay, so this is quite simple, but now we're basically going to do the same thing in gravity. And so this here is what I've just described. Now, what we're going to be looking at in general Covalent series is, well, now we're going to have frames that are associated with a diffeomorphism group. And so they're going to be maps from space-time into something that we can call frame orientation space. So they're also going to have different in and output spaces, just like really the tetrad also has different in and output spaces. And then gauge transformations are really bulk space-time diffeomorphisms. Well, they have to act from the left on this frame, on the space-time side, of course. And now what we can call frame reorientations or symmetries, they'll be acting on the space O here, on the image space. And so they have to act from the right. And because of that, again, these frame reorientations, they're only going to act on the reference frame, but not on the other fields in space-time. So just like, these frame reorientations up here. And now, for instance, if this map R here is a diffeomorphism from M to O, then, it is really a group valued reference frame in the same sense in which this here is a group valued reference frame. So this is something I will be talking about a little bit more and try to illustrate this. Now in gauge theories, we can do something similar. Here, however, the reference frames, there are going to be some functionals, again, from space-time into some kind of local frame orientation space, and this will just be the local structure group in that case. So really like the local gauge symmetry group. And here, if it's a non-abelian theory, then we have to be careful again with left and right multiplication. And gauge transformations, they can be, for instance, the ones that act on the frame from the left and frame reorientations from the right. And then if this thing here is definitely going to be valued in the space-time gauge group. So it's a group valued reference frame. And just to give you a bit of an intuition of how you can realize something like this here, if you have, for instance, some asymptotic boundary with some anchor point x naught, you can shoot in, for example, a Wilson line into the bulk. And now if you look at how gauge transformations act on this, if they act trivially on the boundary, this is a group valued object. So it assigns a group valued object to the end of the Wilson line. And if the gauge transformations act trivially on the boundary, then they will just really act on the whole thing here just by left multiplication. And a frame reorientation would be something like an asymptotic reorientation of your frame, or something like a change of local trivialization. And then you get also something like this. Okay. So this is to provide you a bit of intuition of how one can think of these things as dynamical reference frames. And now I'll be focusing in the coming slides really on general covariant series, so dynamical frames for the diffeomorphism group. And here's an example of how you can realize what I described on the previous slide for gravitational series. So suppose you have a boundary in your space-time, a time-like boundary. And for simplicity at the moment, let's assume it's a finite boundary. Then you can basically parameterize bulk points by just shooting geodesics into the bulk. And this will give you a dynamical parameterization of bulk points, because of course, where you end up depends on the metric configuration. And now, a priori, there's many ways in which you can do this. And this is parameterized by the anchor point on the boundary. So in 4 dimensions, that would be 3 parameters. Then the distance by which you shoot the geodesic in, so this tau, and maybe some boundary vector field that tells you, together with the normal, which direction you go in. So, and for instance, 4 dimensions, those would be 7 parameters that you can use to parameterize bulk points. So that's, of course, more than we would need. And of course, just a reflection of the fact that that there's many bulk points that are connected by many geodesics to the boundary. And so we can call this set of parameters really like a local orientation space, like O that I was describing or mentioning on some of the previous slides. But if we want to really write this thing as a dynamical reference frame field in space-time, what we would want to have is basically where we can at least locally invert the relation between this parameter space and bulk space-time points. And so in order to do that, we have to restrict to a subset of like a lower dimensional subset of this orientation space, such that we can have an injective relationship between these parameters and bulk points. And for instance, you can do it by fixing the boundary vector field. And then you have just the boundary anchor point and the distance by which you shoot in. And you can show that this leads to exactly such dynamical reference frame fields, at least for neighborhoods of bulk space-time points that satisfy these properties that I showed before. In particular, they're gauge covariant under bulk space-time diffeomorphisms in this way here. So satisfying those relations that I showed before. And then you can use these frame fields to really address observables and construct relational observables. Now, there's also, so this here this works in vacuum GR, but we use somehow the boundary as some kind of reference. You can also do things like this with matter fields. Just as an example, there's these Brown-Kukash dust frames. So these are dynamical dust fields in space-time that you can use to specify, for instance, some Cauchy surface, and then instead of having boundary anchor geodesics, you can look at now Cauchy surface anchor geodesics, and it turns out you can find dynamical reference frames in that case as well, and those are really basically just given by 4 dust scalar fields that are diffeomorphisms from at least parts of space-time into such a dust space-time or into an orientation space. And again, they satisfy the properties that I mentioned before. So this here is just to provide you some intuition how things like this can be realized, but there's of course zillions of other ways. And so now if you want to have some more general setup, I'll just give you sort of a one-slide overview of how we treat dynamical frames more generally in general covariant series, and then what we can do with it. So it's a bit more abstract, but an abstraction of what I've just shown you. But basically what we want is, again, these gauge covariant dynamic addressings of local events in space-time. So similar to what well, in the same way in which I already discussed it earlier in the talk and in the previous slides. And in general, there's going to be many different ways in which you can do this. And in order to have a notion of covariance, we also want to have sort of the space of all reference frames. And this we can do by introducing the notion of what we call a universal dressing space that we call D. And it's basically just the set of all such gauge covariant dressings. So that associate to any solution of the equation of motion a space-time point. And they're supposed to be gauge covariant. And maybe the best way to illustrate this is in terms of such a diagram. So this is a sort of horribly abstract object at first. And by itself doesn't give you a nice parametrization of space-time. It is, however, a bundle. And the bundle map, the projection is really given just by this, by the dressing. So that gives you always for any solution for different associated with different points in the dressing space, points in the bulk of space-time. And but in order to have a coordinatization, something like really dynamical coordinates for space-time, we need a parameterization of this abstract object. And here, basically, in order to come up with a parameterized frame, we need something like an additional structure. So something like injective maps from what we call these orientation spaces. For instance, like these spaces of whatever boundary anchor points, boundary vector fields, and distance into the bulk that I mentioned before. So they can be of higher dimension than space-time a priori. And there will exist many different ways in which we can parameterize different points in such a dressing space. And when we connect basically these injective maps with that bundle map, okay, it gives you a new map into space-time that's turns out to be gauge covariant. And again, when we restrict to structures where such a map is actually injective into space-time, so at least into some neighborhoods of space-time, then we can invert this map here on its image. And then it's a dynamical object defined on space-time. So then you can think of it really as a dynamical frame field. And due to these covariance properties, it will have also these gauge covariance transformations of reference frames that I showed before. So maybe that's a little bit abstract, but that's a way in which you can really treat quite generally these dynamical frames or gauge covariant frames in general covariant series. And when we have such structures, and let me emphasize again, in general, there's many different ways in which you can realize such concrete maps in practice, okay? It depends really on the choice of degrees of freedom you have in your theory. And now how do you go about constructing dressed observables or relational observables from this? So suppose we have some kind of gauge, some covariant object, so transformed like this under push forward, under bulk gauge diffeomorphisms. So it could be, for example, a tensor field, doesn't have to be. Then we can construct a frame dressed observable simply by taking that thing and using the frame and pulling back that object from space-time onto its orientation space. And just by looking at how the frame itself and that has a covariance property, and this A also has a covariance property, and they're exactly such that they cancel each other, and you get a gauge invariant object at the end of the day. And now, again, this object is now an observable that really lives. It's associated with the orientation space. It's no longer, for instance, a tensor field on space-time. And again, it is something that's a relational observable. And it will, in fact, answer the question, really, what's the value of, in general, it will be some certain component of maybe some tensor A at some event in spacetime where the reference frame field is in a local orientation O. So, and that's really this orientation is basically the the point in orientation space that this dynamical frame map maps you to, or that it associates with the bulk spacetime point. Okay, and this is really like a generalization of this, what I showed you for the scalar field example at the very beginning in the Z model by Giddings and so on. So this here is something that works really generally. And this is again something that is local now to this orientation, O in orientation space. But since this is dynamically related to a bulk spacetime point, you can also say that this observable is also local relative to a dynamically defined event in spacetime. Okay, and I don't have time to discuss that really any further. But it turns out that this construction here really encompasses, at least to the best of our knowledge, all the previous constructions for constructing dressed observables in generally covariant series, and in particular also relational observables in various representations that have been developed by different communities. And in fact also generalizes them. So to explain that more carefully would take much more time, and I'm just going to throw that at you. And if you're interested, you can look at this paper. Okay, now that we have dynamical frames, we can also consider changes of dynamical frame. So coming to the question of dynamical frame covariance. And so it's probably best described again by such a picture here. So suppose we have now two dynamical frames whose spacetime support overlaps somewhere, and they're injective. And then, of course, the way you can really map from the description relative to one frame to that relative to another is really in exactly the same way as with coordinate transformations. It's just that these are going to be dynamical coordinate transformations, so they depend on the field configuration. So in order to go from the description of frame one, say, you just map from the orientation space using the frame back into spacetime, and then from spacetime back into the new orientation space. So that's really this map here. It's a dynamical coordinate change. And when you actually look at this thing, and you look back, for instance, at this example of special relativity, where I showed you that the frame change map was also a relational observable, that's the same here. If you look at this here, it's really just addressing of the first frame by the second frame, if you take into account that these guys transform like scalars. And so this dynamical coordinate change map is really nothing else than the relational observable that describes the second frame relative to the first, or vice versa. So it means, again, the transformation law consists of itself of gauge invariant relational observables, just like in the special relativity case. And in the case of the geodesic dressings, it has a really nice geometric interpretation. So if you restrict, for instance, to two different geodesic frames consisting, for example, of where you fix the boundary vector field to two different configurations, then this map here really just corresponds to, basically use the boundary anchor point and the distance into the bulk from, let's say, the second frame. And in order to do the dynamical frame transformation, it really just amounts to mapping back to the bulk point you want to describe along the first geodesic, and then out using the second geodesic to the new anchor points. And that's really the geometric picture behind this dynamical coordinate change. Okay. And now when we have these dynamical coordinate changes, so they depend on the field configuration, so on the solution, we can apply them to these relational observables. And what does that really do? It's really just going to transform the relational observables from one frame to relational observables of the other. So for instance, describing, let's say, some tensor quantity T relative to frame one, if we throw this map on it, it really maps it to the relational observable describing the same tensor, space-time tensor, but now relative to the second frame. And so this is a change of gauge invariant description from between different internal frames. And now if you want to have a global gauge invariant description of space-time in general, these frames are only defined locally in space-time, or the support of them. So then we would need something like a dynamical frame atlas. or a relational atlas if you want. And so basically we just need a collection of such frames in such a way that the space-time supports really, where they're injective, cover all of space-time. And then if you have that, then the transition functions between the different frame perspectives are just going to be given by this here. All right. How am I doing this time? I guess about 10. Yeah. Okay. Maybe let me skip the slide here in the interest of time. So this slide was basically just using this possibility that we can have a consistent way of transforming between different dynamical frame perspectives and using it to formulate really mathematically precise statement of that all the laws of physics are the same in every dynamical reference frame. So you can basically just use the usual notion of general covariance to map the equations of motion into different internal frame perspectives and relate them consistently. But I think if I describe that, that might cost me a little bit too much time. So, but you can ask me later if you want. But okay, maybe let's come then to another quite interesting topic, and that's microcausality. So if we, as I mentioned, if you want to have a consistent relational notion of localization, then we should also have something like, well, relativistic causality in terms of relational observables. And it turns out you get it under certain conditions. And so in particular, you get it in the following sense. So suppose you have two relational observables, and what we want is, that if they're space-like separated in a certain sense, then they should Poisson commute. And yeah, so if we have two relational observables, they may in fact be associated with different dynamical reference frames. And what we need to have is that these frames transform trivially under large diffeos. So they should not be charged under large diffeos. And in fact, what you need is that if you remember that these observables are now objects on local orientation spaces. And if we use the frame to map the support of these observables back to space-time, then the statement is if the sort of these relationally defined space-time supports of these two relational observables are space-like separated, then in fact this is true and they commute. Okay. And note that, for instance, if these frames are actually diffeomorphisms themselves, as they are when you have group-valued frames, then these orientation spaces that I mentioned, they have a causal structure themselves because, well, they're just defined by the Drest metric that you get by pushing forward the space-time metric to your orientation space. So there is a causal structure then both in these orientation spaces and of course in space-time, and they're related. But okay, I cannot describe this in detail how this is achieved, but let me just give you in a nutshell how one goes about arguing for this. So here one uses the so-called covariant phase space formalism, and we compute the Poisson bracket for these gauge invariant objects using, well, one gets the so-called presymplectic structure from variations of the Lagrangian, and we contract into it field space vectors that are associated with variations of these observables we're interested in. And basically, you can write it out in components by variations of the presymplectic potential. And what we have inside here are just basically in components written the field variations under these different vector fields. And what you can then do is to use the so-called Payot's bracket. It's a covariant Poisson bracket that is equivalent to the structure on the covariant field space and covariant phase space. And you can show that on shell, we're going to be interested in these variations here. And they come from these different, or associated with these different observables. And what you can show is that you can always choose a gauge in such a way that these variations vanish outside the domain of influence of the space-time support of these observables. And so, for instance, if you're looking at like a scalar field, a relational observable of it, the space-time support would be really like the point in the bulk space-time where you want to evaluate that field. And so that really just means you can always choose a Cauchy slice in such a way that nowhere on the slice do these two variations, are they non-vanishing simultaneously. And since this is linear in both of them, that means that this whole thing vanishes in that case. So this means, these variations, the one associated with the second observable is only non-zero in a certain gauge in this yellow area, the other one only this red area, and then you can always choose Cauchy slices such that that this whole thing vanishes.
The statement hold even if you include the back reaction of one of the operator to the space-time?
Which operators?
Okay, so suppose that we insert some operator O1, let's say, and then, okay, in general, the operator starts to back react to the space-time, and so usually this is the reason why if we compute the quantum commutator between two operators in gravity, there is a necessarily we have this e to the minus s factor, but there that okay this the Poisson bracket always vanishes. So I'm wondering the effect of this back reaction of the operator insertion to the space-time. And
so by back reaction, you mean like coupling it to the action, really?
Yeah.
Well, I mean, so the thing is that in order to compute the Pals brackets, you deform the action by the operators that go, or in this case, the observables that go into the in the brackets here.
Okay.
Yeah. So it is. I mean, in order to compute.
Okay, so maybe you're saying that even if you take into account the effect of back reaction to the space-time, the two operators still commute.
Well, so I mean, the thing is that in order to write down the Pals brackets, you define it really in terms of perturbations of the.
Okay, I see. So this is okay. That discussion with respect to 1 over n expression in the case of CFT.
Yes, I mean, basically, you look at an action where you take the action and then, for instance, minus lambda some parameter lambda. So depending on which order you compute this thing, and then you deform it by.
Okay, sure. This means that the conclusion might be changing if once you include the non-perturbative correction to the field.
Yeah. So the thing is, in order to compute this bracket, you really only need to look at the kind of, well, you look at it at evaluation. So let me write it down. O1, O2. Sorry for my handwriting. It's with my left hand. So for instance, here, this would be defined by O1, and then you evaluate it on solutions. Okay, maybe I haven't completely explained that, but lambda, there's a lambda here, and then, okay, let's deform it by 2 here, and that's the variation associated with the second one, and then you really set this at lambda equals 0. So it's really only the first order that plays into this.
I see. Thank you.
Okay. Okay. So yeah. So anyway, so then you can show that using such arguments. So yeah, this is basically a very rough summary of how you show this. And okay, then this vanishes under these conditions. So that's a generalization of an argument by Don Meroff, where you only use local frames. So in our case, the frames can be non-local. They just shouldn't touch the boundary. So these geodesic anchored frames, when the geodesics are anchored on the asymptotic boundary, that seems not to work. And so that's related to this here. So there seem to be challenges with imposing boundary conditions that are consistent with bulk microcausality when you have frames that are non-trivially charged under large diffuse. So when you want to solve these things here, because you're evaluating it on solutions and you're looking at situations with boundaries, then you have to usually impose boundary conditions to have a consistent variational principle, and there are challenges when these frames are gravitationally charged. And that connects with perturbative treatments by Will Donnelly and Steve Giddings. But what we do here is non-perturbative and classical. Okay, so I think now I'm starting to run out of time. That's the last subject. Can I have maybe 5 minutes? Is that okay? Then, so the next or the last topic is really again about locality, but now we want to discuss notions of subsystems, but defined relative to such a frame. And why do we want to have it? Of course, if we want to discuss engage invariant ways, quantum information properties, or space-time thermodynamics associated with subregions, and look how different subregions interact, or even if you want to look at emergent space-time scenarios and you basically build them up from smaller constituents, then this is something one should be worrying about. Now, there's challenges to doing this when you have gauge transformations. And one thing to note is that when you look at a region and the gauge invariant data in that region, plus the gauge invariant data and its complement, that together doesn't actually encompass all the gauge invariant data in your theory. And that's, for instance, very simple to see if you have groups of particles and subject to translation invariance. If you have one group of particle and you look at all the internal relations and you have the other group of particles, and all the internal relations, and these two groups of particles are like a subregion and its complement, then only the internal relations together are not going to tell me what the relations are between these two groups of particles. And the same is true also in gauge theory and gravity. For instance, if we look back at this Wilson line, dressed Wilson line that I showed on the first slides, if you just cut it by some interface into pieces like this, they're not going to be individually gauge invariant. And it turns out you cannot actually write this composite object in terms of purely gauge invariant data from one side and gauge invariant data from the other side. Okay. And the same is also true, for instance, if you use like geodesic dressings, and these geodesics cut a boundary in gravity, it's the same. And another thing that happens is when you look at, you come from the global perspective, and now you go to a subregion perspective, and you look at the symplectic structure, and you look at transformations that are gauged with respect to the global theory. When you now look at those for the subregion theory, and I just cut it, they turn out to no longer annihilate the presymplectic structure, so they don't correspond to degenerate directions I'm going to factor out when I build a physical phase space. That means in particular that these transformations, so those would correspond to gauge transformations that have support also on the boundary, that those become physical in a sense. And in gravitational series, it even turns out that they are not in general integrable, and that makes a lot of physical sense. If you have diffeomorphisms with support on the boundary of your finite subregion, and they act transversely to the boundary, then it changes what you mean by a subsystem, and it corresponds to something like an open system dynamics. And now there's other ways in which you can actually remedy the situation or improve the situation and really formulate it in a purely gauge invariant way. That was noticed at least by Donnelly and Friedel. And that's, you can remedy this by introducing a certain phase space extension. So for example, if you just assume now here in this case of the Wilson line, that there exists some new group valued field on the interface, then I can decompose this in gauge invariant ways. So as before, these individually, what I cut is not going to be gauge invariant, but if I dress it with this group valued object locally, then I can decompose it into two gauge invariant objects. And so that's just as an example. And it turns out when you look at presymplectic structure now in this extended phase space, depending on how you do it, you actually can find ways in which you get dressed symplectic structures such that gauge transformations that are gauge transformations in the global theory remain still gauge transformations even for the subregion. And they also showed this for vacuum general relativity. You can do something similar. And if you introduce something like a dynamical coordinate system. And so this has really triggered a lot of research on finite subregions in recent years. There's been a whole wave of works on this. But one thing to note from our perspective here is really that this field U here is, it's group valued, and this dynamical coordinate system, they're really nothing else than dynamical reference frame fields in the same sense in which I've discussed them in this talk. So here in the way they have been introduced, it was a bit they were postulated somewhat rather abstractly. So you had to add them by hand. And basically, what I want to describe now is how you can actually realize them more concretely in your theory from the point of view of the global theory. So these previous constructions, they only looked at a subregion and kind of forgot about the global theory. And what we want to do is come rather from the global theory and then find structures within the global theory that recover all this, what was introduced before, without having to postulate these structures or introducing them by hand. And this can be done. I guess I should be somewhat quick. Let me just give you a bit of intuition. So the way you can, what I should say is these additional reference frame fields, they're sometimes called edge modes. Okay, so they're like in the gauge theory case, they live on the edge. And now, for instance, in gauge theories, the way you can realize these edge mode fields is by shooting in, let's say, from some asymptotic boundary, Wilson lines that end on the finite boundary that you actually care about. So, and then really similar to what I explained in some of the earlier slides, that gives you, a group valued field on the finite boundary. And in fact, it turns out it really satisfies all the conditions that you would want. In gravity, you can do the same thing with geodesic frames and the like boundary anchor geodesic frames. And the way you can really interpret this is then that, so in both cases, they give you really exactly what you want from the point of view of the local theory. But from the point of view of the global theory, they're not new degrees of freedom. But they're rather, you can think of them as internalized external reference frames for the subregion. So they originate in the complement. They're non-local objects, and that turns out to be important. But since they originate in the complement, when you look at the framed rest observables or the relational observables on the boundary, what they really describe is how that finite subregion relates to its complement. So that's also somewhat important. I should be finishing. Yeah, okay. Okay, yeah. Okay, I should then be cutting the rest. Anyway, one can also show that, for instance, then you get no unique edge mode fields, so you run into the question of frame covariance. And okay, you can use this picture to also have a nice physical interpretation of boundary charges and so on that you can interpret in terms of these frame reorientations that I described. Okay, you get nice corner symmetry algebras. Sorry, it's not moving. Okay, then the last part was also relating to the subregions. It turns out that the notion of the subsystem becomes frame relative. And in particular, also the notions of thermodynamical properties or correlations, and even whether it is in equilibrium or not, that depends on your choice of frame. That also relates to quantum reference frames. But yeah, I guess I don't have time to discuss that. So yeah, maybe I just leave the conclusions here and let you read it, and I'll finish here. And thank you very much for your attention.
Thank you very much. Very interesting talk. So, do you have a question and comment?
So I have a question about your X5. It's the coordinate.
Oh yeah.
Yeah. So do you have some explicit example, but assuming some, for example, free scalar or?
Yeah. So yeah. Okay. So sorry, it's further back. Yeah. So okay, maybe I didn't explain it carefully enough, but for instance, this here gives you examples of that. So these boundary anchor geodesics, when you address the bulk points, you describe them in terms of this boundary data, by how far you shoot in a geodesic, what's the boundary anchor points, and the angle. Then that of course gives you a point in the bulk. And in that case, phi is just the metric here if it's in vacuum GR. So, and that is an example where you get something like this. And it turns out that this here, you can show that this transforms in exactly the way that you want.
So I thought the phi is a scalar field. It's
sorry.
because
no, sorry, maybe no. Okay, maybe that was a bit confusing. I used this two different notions of phi, and one was collectively all fields. So here maybe, so I'm very sorry about my notation then. So this here is really a collective notation for all fields, including metric, whatever you have in the theory. And for scalar fields, I just use this phi, I'm sorry.
I see. Thank you.
So then, yeah.
Another question, if we use this, Wilson line-like formulation, as you explained, do we get, do you have some idea how edge mode looks like, about especially for when we quantize it?
Well, I mean,
maybe you may mention some very quickly. You mentioned some algebra or.
Yeah. So okay, there's different. So sometimes people mean different things when they talk about edge modes. So and maybe I should clarify again what I meant by it. So edge mode here, I meant really in terms of the new dynamical, from the point of view of the subregion, the new degree of freedom that is not gauge invariant by itself, but that is like a like here this U that is the dynamical frame, But sometimes people call the charges that you compute on the boundary using those dynamical frames. Sometimes they call those edge modes, where the charges themselves are, however, gauge invariant. So, so these are two different things. And here, yeah, a concrete realization of edge modes, for instance, Young-Mills theory or Chern-Simons or whatever. Yeah, at least classically, you get it by those Wilson lines. I mean, that's I would say it's an explicit realization of these abstract ones that have been postulated before. And in particular, it tells you also, when you come from the point of view of the global theory, that there's no unique way of assigning an edge mode. You can have many different ones, so many different frame choices. But then maybe about your questions about algebras, yes. So you can. So I didn't really have time to discuss that. So here I only do it for gravity, but in another paper we also do it for gauge theories. You can basically what you have to do is you have to construct a presymplectic structure for your subregion, including the new frame field that's there, and we give an algorithm for doing so that gives you an unambiguous subregion structure that's gauge invariant, devoid of these ambiguities, JK ambiguities, if you know about that. And the way we construct this is by requiring that the presymplectic structure of the subregion is preserved under the dynamics. And then in order to get the charges, you have to look at the contractions of that presymplectic structure with the field space vector fields that correspond to reorienting your edge mode frame. And then for gauge theories, you can really reproduce the usual charges that one gets in a gauge invariant way. Okay, maybe you want to call those edge modes, but those charges you can all reproduce in this way. And in the gravitational case, it's likewise like this. So again, well, it's a bit more subtle, but in the gravitational case, we now have the additional complication that well, in gauge theory, the geometry of the region is given before you define the frame. But in order to define the subregion in a gauge invariant way, in gravity, we have to even say what the frame is. And so basically we have, of course, the space-time M itself and the orientation space, and we can look at the subregion in both. And we have these space-time diffeomorphisms and the orientation space diffeomorphisms, and they have different actions. So it's whether they act from the right or the left, these diffeomorphisms. And the ones that act from the left are space-time diffeos. And they, when you contract them into this presymplectic structure, they just give you the usual constraint algebra. So really a consistent representation of the algebra of vector fields, space-time vector fields on your phase space. But maybe somewhat more interestingly about the charges you were asking for is when you look at field space vector fields that generate transformations like this, they should be tangential to the space of solutions. But then whether you get nice charges or not depends again on whether these diffeomorphisms on the orientation space, whether they're tangential to the region or transversal. If they're transversal, you get open system dynamics, non-integrable charges. But when they're tangential, then when you impose boundary conditions, you get a corner algebra. So a corner symmetry algebra, and in this case, you get one that's actually centrally extended. And this the centrally extended algebra that we get is a relational or frame-dressed version of something that has been proposed by Chandrasekaran and Speranza 2 years ago. They didn't use edge mode, so this was like a gauge fixed construction, but here we recover it in a gauge invariant way. Yeah.
So this, I mean, maybe we can explain entropy using that algebra.
Yeah, yes. So I mean, that's for instance something that Chandrasekaran and Speranza started looking at in that paper. So we didn't go further on this, but in principle, yes, because then you can start counting degrees of freedom on the boundary that might be relevant for entropy search right now.
So to define you have this coordinate field x5, so you need some boundary.
No, no.
Starting point.
No. So
you can do it without.
Yeah, you can do it without boundary. So it's just this boundary anchored geodesic case is particularly intuitive. That's why I mentioned it. But you don't need boundaries in general. You can have matter fields, for instance, and you can use matter also as a reference. Yeah. So yeah, no boundaries are needed. Okay.
Time is running out. So we may have quick question and comment for online audience. Oh,
But if there are questions from online participants, then okay, I can skip it. Okay, so my question would be that is it feasible to compute the correlation functions of these operators?
I don't know. So I mean, this is purely classical what we've done here.
Sure.
So in the quantum theory, yeah.
Okay. Is it okay? Is there any sense that it looks like a correlation function of local operators plus some, corrections to it?
I would think so, but yeah, I haven't really looked into this.
Okay.
But yeah, one thing that's important is even also in the quantum theory is that okay, it's something only touched on is that the correlation functions for subregion properties are going to be dependent on the choice of dynamical frame, as are going to be correlations. So even entropies that you associate with a subregion depend on the definition of your frame.
I see. Okay, can I ask one more question? So you said that okay, you can use this. I mean, that the formalism for the case of closed universe as well. If you use this dust frame, what do you do you use this? I mean, the structure of this path to infinity in the discussion?
Yeah. So okay, there's a subtlety here. So I didn't have time to discuss this for the subregion stuff.
Mm-hmm.
No, actually, yeah. So there you could use the dust frame, but you cannot use the dust frame directly to define the boundary, the finite boundary. What you would have to do, and it turns out you always need some non-locality of the frame. But what you could do is you have the finite subregion you're interested in. You can look at another finite subregion that is larger and contains it. And then you define that larger subregion relative to the dust frame. And then from that larger boundary, you shoot in geodesics to define the smaller subregion. So this you can do. So it sounds at first a bit complicated, but you need for the frame to be somewhat non-local. And the reason is the non-locality ensures that it has support in the causal complement of the subregion where you're interested in. And that allows you to kind of gives you enough wiggle room to change the initial data outside, in the causal complement of the subregion you're interested in such a way that, you change the configuration of the frame without changing the initial data of only the degrees of freedom inside your subregion. And so, and that you need in order to really treat the frame as a completely new, dynamically independent degree of freedom on the boundary of your finite subregion.
Oh, I see.
So, but you can do it with the dust frame, but then you need to define the other boundary from which you shoot in the geodesics. Then you would have to define that.
So for example, in the case of this closed universe, you have to attach it to some heat bath surrounding the closed universe.
If you wanted to do something like this here, yeah. But for instance, just in this general construction, when you don't care about finite subregions, you just look at dynamical frames. Then yeah, you don't need boundaries at all. I mean, that's if you have matter frames such as the dust frame, there's no need for a boundary.
Sure, thank you.
Any other question or comment? No. So online audience, do you have a question or comment? No. Okay. So time has come. So we would like to thank the speaker again. Thank you very much.
Thanks for your attention.